Hello and welcome to the second lesson of the Chem Gems. Today we will be covering atomic structure, and we have changed the layout of our video a little bit due to requests from our fellow Gen Zers. So let's get started. So today it's atomic structure and we'll be covering some basics. First of all, the notation and composition of the atom. So as we've mentioned before, the smallest part of an element is an atom. It used to be thought indivisible, but is now proven that they can be broken down into subatomic particles. So here let's switch a little bit to sort of the history of atomic theory. So first, in the ancient world, we've had Democritus, who theorized atomos. He thought that things were basically made of different things. So, for example, like this cube is made out of distinctly unique cube atomos, and Chilgai is made out of distinctly unique Chilgai atomos. Then we've got John Dalton, who came up with the billiard ball. So basically, he thought that basically all things were made up of different types of spheres, balls, yahoo. And then with J.J. Thomson, we have the plum pudding model. So this basically states that there's like this giant charged body of protons and electrons, which are positively charged and negatively charged, within a particle, and then they're embedded within each other in this giant plum pudding. They've also called it a chocolate chip cookie model, I think, but yeah, let's just call it plum pudding. Then we have Ernst Rutherford. Couldn't be bothered to write Ernest. So basically, he came up with the idea that there is space between positive charges and a central nucleus. So basically, in a central nucleus, you have positive charges, and then you have like electrons sort of like floating around in orbits. But the most important thing is that he found out that there's a nucleus and that there's space between it. So how he found out about this was through an alpha scattering experiment that some of you might heard of before. So basically what happened was he had the particle, and then he shot them with alpha rays through a gold foil, and then what he noticed was that some of the particles that he shot ricocheted back. Some of them went through, and it wasn't a lot of them ricocheted back. And so this led him to theorize, why are some of them passing through, but some of them are bouncing back? So, because, technically, if we followed the plum pudding model, everything should not like go through, right? Because there's like no space between it. But then he found out that some of them went through, which means that, there's got to be space in between it. So that's how he came up with this model. Okay. Now we're moving on to Niels Bohr with the planetary model. So the Bohr diagrams are the types of atomic models that we'll be frequently using, even though it's not quite accurate, as perhaps you'll learn later on, but this is the type that we use to draw like simple diagrams first. So basically, he's the guy who said that electrons are restricted in circular orbits and they have different energy levels. Then this is currently the most modern atomic theory or model. It's the quantum model. So this was like thought up by people like Schrödinger with his cat, and Einstein. So this is basically what the particle would look like. Because they theorized that electrons actually exist in clouds, and you can't really exactly tell which direction, which way that they'll be traveling. So this is just, electron cloud. Not quite sure what's going on, but that's what quantum is. Okay, let's go back. So all atoms except for hydrogen, which is an interesting case, are made up of 3 subatomic particles. So you have protons, neutrons, and electrons. Protons are positively charged. Neutrons do not have a charge, and electrons are negatively charged. Atomic number, so this is the number that you would identify on a periodic table, and this is also signifies the amount of protons in the nucleus of an atom. So it defines which element the atom is and gives its position in the periodic table. Mass number, which is on the top here, this is the total number of protons plus neutrons in an atom. And then for nuclear charge are basically mainly used for ions, which are charged particles for elements or compounds when electrons are lost or gained. So this is where it sometimes gets a little bit tricky. So when electrons are lost, remember that electrons are negatively charged. So when they are lost, the ion should have a positive charge. When electrons are gained, they should have a negative charge because you've gained one negative charge, so they're negative. So with that, positive ions lose electrons and they're called cations, and negative ions gain electrons, which are called anions. I think like the most common way to remember it is it's like I'm positively certain, positively certain I like cats, or you can say I'm positively certain that I don't like cats, but then that's such an unpopular opinion, so yeah. And so with this, with knowing the atomic number, mass, and element, so here is how you would notate a particle, an atom. And then with this, you can actually determine the amount of neutrons within an atom. So the amount of neutrons is equal to the atomic mass, which is basically A, minus the amount of protons. So that's how you would get the amount of neutrons. As for the amount of electrons, this depends on what the atom exactly is, because if it's an ion, then the amount of electrons will differ from the amount of protons. However, it's a neutrally charged atom. Usually it has the same amount of electrons and protons, except for isotopes. So for isotopes, we have the same number of protons but a different number of neutrons. So basically it's the same element, the element has the same name, but then you have a different amount of neutrons, and therefore the mass will be different as well because you have different amount of protons. So therefore they have the same chemical properties but different physical properties. That's because they react in the same way and that they have the same number of electrons, because the electrons are the subatomic particles that are most engaged in chemical reactions. And then electrons determine the chemical reactivity, and the different masses impact physical properties such as, melting point and boiling point. It affects how much energy is required for these isotopes to change states. So one example would be hydrogen. So for hydrogen 1, you have one proton here in the middle, and then you have one electron. Mass number is 1. And then here you have hydrogen 2, which has one proton and one neutron, and again with only one electron. So this is also called deuterium, hydrogen 2. And then you also have hydrogen 3. So this has one proton and two neutrons. I'm just going to write neutron times 2. Hydrogen 3, and this is also called tritium. And you see the difference because, so for hydrogen 1, the mass number is 1. For hydrogen 2, the mass number is 2. And for hydrogen 3, the mass number is 3. So therefore, they also have different boiling points due to their different weights. And then relative atomic mass. The atomic mass reported on the periodic table is actually like just an average of, based on natural abundance, like the weight, I keep saying weight, that's not very scientific, the mass of elements that we find sort of in the natural environment. So all of it is relative to a carbon-12 atom. And when we mean carbon-12, 12 corresponds to the number here. So basically, its mass is exactly 12 grams. Therefore, 1 unit of relative atomic mass is 1 over 12. So to calculate relative atomic mass, we need to know the natural abundance of the item. So here we have a example question. Lithium has 2 naturally occurring isotopes. Lithium-6 has a natural abundance of 7%, and lithium-7 has a natural abundance of 93%. Assume 100 atoms. So here the natural abundance would basically be 7% multiplied by 6, because its atomic mass is 6, plus 93% times 7, because it is lithium-7, the mass is 7, and divided by 100. So this is like in math how you would usually do an average as well. It's like total amount of numbers divided by the total amount. As you can see here, 93 plus 7 is equal to 100. So yeah. And then you would have 6.93 atomic mass units. And that is pretty much all for atomic structure. Thank you for watching this video, and thank you to my partner for making this slide deck. See you next time.